But, of course, there's more to spontaneity than just looking at the E values. We can actually correlate the E values to the Gibbs free energy. So in order to convert back and forth between Gibbs free energy and voltage, we would use this equation right here. Nothing really too new in this reaction. The only thing really different is this Faraday, so F, that's the Faraday's constant we talked about at the beginning of this unit, 96,500 coulombs per mole of electron. The E right here is the E standard, and it matches up with the delta G standard. So in both cases, we need to be at 25 degrees Celsius, 1 molar concentration, 1 atmosphere of pressure. Do note, though, there is a negative sign on this reaction, and so it's going to be the negative to get our delta G. And N is the number of moles of electrons transferred in a balanced chemical equation. So when we balance out the reaction, how many moles of electrons are transferred from the reduction or oxidation to the reduction. And of course, I'll show you an example. So this problem right here, we're given a reaction, and it wants us to find the delta G and, ooh, the equilibrium constant as well. So this should be fun. And to do the delta G, which we'll start off with, we can use that equation that we just saw. And it looks like we're going to need the E of the cell first off, so let's start by getting that. This is just going back to the old formula where we add the two together. And so we can see in our reaction that we have chromium 3 plus turning into chromium solid, so just like this one's written, so that one's going to stay as our redox reaction. But then manganese solid is turning into manganese 2 plus, and so this reaction right here is going to need to be flipped. So then we have our new voltage values of negative 0.74 and 1.18. And that puts our voltage at 0.44 volts. So that'll be the number that we then use for E. Now Faraday's constant, 96,500, we already know that, but then the N, so the number of electrons transferred. So for that we need to look at the half reactions again. We see right here that chromium took in 3 electrons when it was reduced, and manganese gave off 2. Now that doesn't fit because we can't have 2 electrons transferred and then 3 electrons used. We have to make those match, and in order to do that we'd have to multiply. And so to get those 2 to pair up, multiply this top one by 2, we multiply this bottom one by 3. And so what that's going to mean is that we're going to have 6 electrons transferred. And so when it's balanced like this, 6 electrons oxidized, reduced, that's going to be the number that goes in for N, 6. Just coming over to a blank page so I have more room. Plugging those numbers in, so it's 6 moles of electrons with that negative on there. Faraday's constant, 96,500 coulombs per mole of electron. And what that lets us do is cancel out moles of electrons. And then 0.44 volts. Remember we talked about when we talked about voltage, voltage is the same thing as joules per coulomb. And so then that allows coulombs to cancel out coulombs. And we are left with our units of joules. So calculate that out and we get negative 250,000 joules. Let's put that into a more reasonable number and write it as negative 250 kilojoules. So negative delta G tells us that this reaction is thermodynamically favored, which we were already able to see from the positive E value. And worth mentioning, since we're talking about an equation is balanced with moles, both of these values are going to be joules per mole. So it's joules per mole or kilojoules per mole of that particular reaction. But we're not done. They also want to know what the equilibrium constant is. Oh, but Mr. Jones, we don't know how to find the equilibrium constant from the voltage. No, but we know how to find it from the delta G. We got to go back a little bit, but we can remember that delta G is equal to the negative R times T ln of K. Oh yeah, I remember that equation now. So we can rearrange it just like we learned. We're going to use the negative 250 joules per mole for our delta G, because remember that R is 8.314 joules per mole Kelvin, and so we need joules and joules to cancel out. And then for temperature, we need to make sure that it is in Kelvin, so it matches up with our R again. And since these are standard states with a little 0 right there, it means it's 25 degrees Celsius or 298 Kelvin. And so then if we plug all of those numbers in using our anti-natural log, we are going to get 6.6 times 10 to the 43rd. And so what this means for us, a very, very large number, well above 1. for our equilibrium constant, so that means our reaction lies extremely towards the products. So products are favored in this reaction, which makes sense. It's spontaneous, which means it goes forward towards the products. We verified that with the E of the cell, we verified that with the delta G, and now we're verifying it again with the equilibrium constant. That shows a large number of products.